This meeting is being recorded.
Okay, so let's start. Rendering algorithms. Rendering is equivalent to measure flow along passes through an infinitely complex light transport graph. Yeah, makes sense. This chapter develops the concept of this graph and some common terminology and notation for describing passes within it. It then surveys some of the most popular photorealistic rendering algorithms. In each case, I cite the seminal publications that introduced the algorithm. Yes. There have since been hundreds of papers refining those techniques, usually by increasing performance at the expense of complexity. Really? I feel like the opposite is also true. The opposite probably is true for the more of the time, increasing complexity by decreasing performance.
Yeah, my intuition is the dumb solution is less performant but a better result. So I get my thought is that conforms with you want something that's more complicated to shave off fractions of a percent over the dumb naive solution that you start with. But
yeah, but I guess if it's compared to Kajia's,
yeah,
really brute force path tracing, everything is increasing performance. The transport graph. So thus far in this note, I presented the model of emitters, light, surface, and camera in concrete geometry settings as shown below. Yeah, we have an emitter, emit some light source that hits some surface, and then bounce around until it hit the camera. Now that we've derived the render equation and built mathematical models of light transport, scattering, and image formation, I ask you to consider the topology only. That is, to abstract the scene into a transport graph. I don't think this way before. The nodes of the graph are points on surface at which light is emitted, scattered, absorbed, and measured. Nodes that emit light are sources, and nodes that absorb light are sinks. Yeah, that makes sense. Edges are line segments along light rays between the points represented by nodes. Light transport passes through this graph. What? That light transport passes through, yeah. Light transport passes through this graph. The passes that affect the image are ones that begin at the source and terminate at the point that is observed by the camera along the primary ray. For one source and one such point, the graph looks like this. Oh yeah, it's just one source and one such point, because camera is an image plane, so it can have multiple points. Also, we have multiple light sources, so it is actually more complicated than this.
Yeah, and the next paragraph explains how there's like infinite number of edges. And so it's just, that graph is basically showing how there's an infinite number of bounces.
Yeah.
per bounce. And it recurses infinitely.
Yeah, infinite number of edges are adjacent to each node. They also arbitrary long passes through the graph. We can at least ensure that there are no cycles by parameterizing nodes by both time and location, so that the same point in space may appear as multiple nodes depending on when the photon hit it. Yeah, that makes sense. One numerical approach to rendering is to select a subset of passes from source to camera pixel and compute the amount of light transported along these. Yeah, we cannot do infinite, so we can only select a subset. This is an estimation of the true amount of light. As one increases the number of passes considered, the estimate should ideally converge to the true amount of light. Unfortunately, there are infinitely many passes, and it could be the case that a single pass transports all of the energy. This is a typo.
Yeah, that looks like a typo.
The error of the estimation is unbounded for arbitrary cases. What does it mean?
Is that whole word just supposed to not be there?
I think it's supposed to say sum of the error of the
Oh,
estimation.
some of the error of the estimation is unbounded. Yeah.
Or yeah, maybe that sum is supposed to not be there. I'm not sure.
But we can design algorithms around heuristics and some assumptions of the broadness of passes or surfaces so that they produce reasonable results for common cases. A large family of rendering algorithms sample light transport passes by casting rays. That's ray tracing. We're already seeing the simplest of those schemes, which is direct illumination with shadow determined by raycasts. The diagram below summarizes 5 ray-based rendering algorithms. Each diagram has the thin red line shadow ray cast between specific node points. The thick black lines represent recasting in random direction to cover points in much the same way the primary cast. These algorithms are explained in more detail throughout the chapter. So direct illumination, that's what the usual rasterization pipeline is done by default. Weighted. Oh, we have one person in waiting room.
So the weighted ray tracing one, that's where you directly sample the lights, right? That's what it's showing for each hit.
Well, that's the next one that's cut off.
Is that? Or
Well, it's,
Oh, sorry, what you said?
like with weighted, that's the one where you are like the next event estimation, right? Where you're like directly sampling the light,
No,
or
not next event estimation. Weighted style is pretty much you trace a ray to the light directly and then see if it's visible.
that's what a next event estimation sort of is.
Yes,
Yeah,
in a
but
way.
I think
that has
weighted is
statistics.
still it's add contribution from direct illumination and from those recursive cases. So I think
Yeah.
in that sense,
the thing about the next event estimation is that gets into statistical stuff, whereas WID style is like 1984 direct lighting only. It doesn't have any of the soft shadows. Like it's very hard shadowy because it doesn't have an estimate.
Yeah, but it's still kind of is a probabilistic.
Yes, but you often are you split the ray in half. Like you do
Yeah,
40%.
just half, just really brute force this kind of way.
So you're
And
not
like-
really taking like the BRDF into account.
Not necessarily, but like if you hit a surface that's semi-glossy but diffusey, semi-reflective versus semi-diffuse, you do two rays. You do a ray in the specular direction, you do the diffuse component separately, and you just multiply it by the percentage that you would expect. So if you went through glass, that's something that's where you do like 40% ray goes on the reflected and then 60% goes in the transmitted, and then you just add them together and multiply after multiplying by the contribution. Whereas a path tracing typically isn't doing ray splitting like that.
Right. Yeah. Okay.
Yeah, so weighted wind problem is that it's not really cheap, and it is very cheap, but if you have a lot of like transparent materials, it can just become insane because it keeps splitting. And this is brute force path tracing. And bidirectional. Path tracing with photon mapping. I guess this is outside of my knowledge now.
My understanding is it's kind of like if you're familiar with like light mapping kind of idea, where it's keeping the lighting intensity on surfaces, basically like a texture.
Okay.
Have you guys looked at Lumen, like from Unreal?
We did have a meeting where we looked at that.
Yeah, I think that's what they're doing, right? They sort of the illuminance cache or something. Like it's a 3D voxel based, thing about like where the light is in the world. I think that's what they mean by photon mapping. I could be wrong though.
Okay.
I think that's one of the techniques that they're using in Lumen. Or it's like Lumen's actually like a combination of a lot of different techniques.
Yeah.
When the transport graph is abstracted in this way, you can see that these rendering algorithms correspond to search algorithms. Yeah, that's true. It's kind of breadth first search. This is because search optimization and numerical estimation are equivalent problems, and the rendering can be approximated using algorithms from any of those areas. There are also rendering algorithms that do not depend on sampling along rays. I sketched two of those in this chapter. Do not depend on sampling along rays. What's algorithms like that?
Yeah, I'm curious what he means by that.
Yeah, that's it. Path notation. Path notation describes classes of light transport passes and subpasses using regular expression and grammar. Could he talking about rasterization? I think rasterization is covered in this case.
Yeah.
I mean, Technically, but that diagram was showing actual rays being casted, right? Like rasterizations, no rays involved. You're just mapping the
But
geometry.
still, it is estimating a recast.
Yeah, but that's not doing any recast, right? It's just mapping geometry directly onto a grid.
Yeah. Using regular expression grammar, I've never seen that. It is primarily used to discuss strategies for sampling those paths and does not directly manifest in a software implementation. Path notation was introduced by Hagbert and later modified by Rich. Oh yeah, this is this famous thesis. Not that, but Metropolis light transport. We probably need to read this. If it's a paper, then we can read this. For that thesis, maybe later. After we have done with PBRT, maybe we can do that thesis. I modify the definitions of path node types slightly so that they can correctly describe paths observed in the real world. Classic path notation names a node by the material present and is limited to certain kind of idealized materials such as perfect mirrors. I instead use it to describe the way that a photon is observed to scatter and make no determination of why the photon scattered in that way, or whether another photon immediately behind it would scatter similarly. Okay, I think I just want to say what the notation looks like. Node types. Path notation describes 4 kinds of nodes that can occur along a path, each of which is abbreviated by a capital letter. So L, S, D, E is I. D is diffuse, specular, luminary, which is light.
Interesting. It separates it from specular and diffuse.
Yeah.
Oh, weird. So it's
Since path is that's probably what he said here is that he doesn't separate it by material, instead by separated by how the photon is scattered. These passes that terminate in absorption of light do not affect the image. There's no symbol to denote the node at which the photon is absorbed. The path is represented by a string of letters. For example, the string LDDE describes the set of passes that begin at emitter and at camera and are scattered in arbitrary direction exactly twice along the way. Variables may also be included in the string, such as LDXE. The passes from an emitter to a surface at which arbitrary scattering occurs, to a surface at which scattering of type X occurs to the camera. Oh, and then there's this regular expression.
Now I see why they need regular expressions, because it could be very long paths.
Yeah.
And depending on how many bounces, yeah.
Square brackets are used to grouping and order of operations. That's not like normal regular expression notation, right? I think you should use parentheses for this kind of stuff. Whatever.
I think it's just you can also use them for order of operations if you're already using from the normal use. So you could like put that star and that applies to all of the square brackets. But yeah, that's not really like the intended point of square brackets.
I thought it was.
The square brackets, aren't those like anything inside? It's like one or the other. It's like these are the set of options, whereas parentheses
Well,
are...
the other is this bar, but
Yeah.
how to group, I think usually is using the parentheses.
Yeah.
I was taught from my compiler class it was brackets for like any of them, and it was more from a directed graph, not a directed graph, but a state machine than text pattern matching. So we didn't really do much of the interesting things you can do with regex with backtracking and all that. It was all just straightforward parsing of stuff.
Yeah, isn't it like square brackets? If you have them like A, B, C, D inside of it, it's like one of those.
Yeah.
Right. It's like a OR operation, a set OR operation.
Yeah,
Yeah.
maybe I'm wrong. I'm really rusty with regex.
Maybe it's just different flavors of regex.
Yeah, that's annoying to do.
I've only recently become familiar with regex. I found a search tool that, using it for word boundaries.
Yeah, that's regex. Well, one website is really good.
Yeah.
So every time I use regex, I use that website.
Me too.
What's the name of the site?
What?
Oh, you said that there was a website for regex stuff. Oh, awesome.
Yeah.
There's several sites like that for testing your
Yeah.
regex.
Yeah. Every time I just Google regex online and find one of them.
Exactly.
I've been meaning to
Yes, so we can input some random stuff and then do some testing. Wait, why is that? Oh, this is the end. Let's just get rid of this dollar. Yeah, that passed. So basically, that's the idea.
Cool.
And if we input something wrong, then it's just now it's a partially match, but
I think you can add
not
a
match the whole string.
I think you can add a slash at the end to make like they have the GM. So if you do like /G, I think then it. Okay, never mind. Yeah, I guess you have to do it. So oh no, it's at the end of the text box. Okay.
I think it's interesting in here. They're talking about caustics passing through a specular thing here, and I guess they're talking about specular refraction down in the caption of one of the images here.
Yeah. Some commonly observed illumination phenomena are created by specific classes of patches. This is just light directly hits the eye. Direct illumination is just one bounce. Caustics is a bunch of 0 or more scattering specular.
That's one or more.
Oh yeah. One or more specular and followed by the end is diffuse.
Caustics only happen with one diffuse. bounce after?
Well,
guess that
there's
makes
some
sense.
surface that it's shining on, right?
Yeah, I guess that wouldn't really make sense if it scattered again.
Well, it does scatter again, right? I mean, you
Right,
can have,
but you just wouldn't notice it, right?
yeah. Well, unless it's a mirror, right? Then you would definitely notice it. You can have
Oh yeah.
mirror, like in a camera or something. You have a whole series of mirrors.
Well, that's true. So yeah, I guess you could have another S plus in there or S star in there.
Reflection and refraction is light followed by a bunch of just random paths around, but at the end is a bunch of specular for reflection or refraction.
This just seems really complicated for something that it seems simple. Light bouncing off a surface or passing through it, and
It's kind of an interesting way to partition like the set of all possible paths from light to camera. That's
I guess if you were using a different algorithm for different types of phenomena or whatever.
because I know that
Yeah.
to do like caustics and stuff, sometimes like forward path tracing makes a lot, or bidirectional makes a lot more sense because
Mhm.
you can represent that better. So maybe something to do with that.
Yeah.
Diffuse interreflection.
It's what is it? Oh, global illumination is if you look farther down, that's what they mean.
Yeah, this is two or more diffuse. And
I'm curious why
here's a bunch of specular.
Okay, it
Sorry,
says
what?
it's zero more specular bounces. So that makes
Yeah.
sense. Okay.
The direct illumination chapter describes how to evaluate light that is emitted directly to the camera and light due to direct illumination passes. Caustics are the bright shapes created when light is focused by reflection or refraction onto a surface that reflects it diffusely. They can literally burn the surface on which they fall. It's like this area. Diffuse interreflection is visible in the red and blue shadows of the ball on the floor and the yellow from the ball onto the white ceiling in this photograph.
It's a real life Cornell box.
Oh,
Yeah, it looks that way.
If diffuse interreflection is here, and
on the ceiling
from the
with the
ball
yellow.
onto the white ceiling. Diffuse interreflection is bunch of specular and two or more diffuse. So it's like there.
So I guess it's just anywhere where the color has transferred onto a different surface, pretty much.
Yeah.
That makes sense to me.
I don't think I've ever heard of this path notation thing. This is new to me. This is cool.
Yeah, it's new to me. The rectangular caustic on the ground is due to bright sunlight specularly reflects on the metal door in this photograph. So caustic is when diffuse. The final way is a diffuse, but then before it's specular.
Mm-hmm. And so it has to hit a diffuse surface, and so then it's the caustic on that diffuse surface. That's okay.
Makes sense.
So I guess like one interesting caustic that we don't think about is like a projector, like a movie projector or something. It's like a caustic that's in focus. And
Yeah, I guess so. Weird.
Yeah. Mirror reflections and the perfect reflection of images seen in shiny objects and to transparent ones. Diffuse interreflection, also referred to as color bleeding, occurs when bright light incident on a relatively matte surface then illuminates another matte surface. When a photographer uses a white card or umbrella to splash light on a model, he or she is leveraging diffuse interreflection. The walls of the canal box are painted with saturated color so that diffuse interreflection onto the neutral floor and object inside is clearly visible. The two most commonly recognized phenomena cannot be neatly described with path notation: shadows and highlights.
Yeah, that makes sense too.
There are no shadow rays in the path notation. We perceive a shadow, or more properly, a region to be in shadow, where other nearby regions have much greater illumination. Path notation can't describe this for two reasons. First, it depends on many passes, and the notation is described by class that a single path belongs to. Second, it is a relative way to describe illumination, and path notation is absolute. For example, an interior room of a building is entirely in shadow of the roof with respect to the sun. Half of the earth is also in shadow with respect to the sun, but you probably won't describe everything at night as being in shadow. You can. Highlights are glossy reflection. They are observed when a large number of different transport passes share a node and also reflect into directions near, but not precisely the same as the mirror. This is the action of multiple different transport passes, so there is no perceived way to describe them using path notation. Yeah. Because path notation only describes one path. Direct and ambient illumination. Computing only direct and emitted illumination is a simple approximation to the rendering equation that always underestimates illumination by considering only these direct transport passes. That's why we add the ambient term to compensate this underestimation. The computational advantage in doing so is that forcing only point light sources, it reduces the render equation to the sum of a small finite number of terms. Yeah, it just becomes a sum. Where beta is the biradiance from the emitter at Y to point X. Yeah, they need to use this biradiance because we can't use radiance for this one for point light. And the visibility function, V by X is 1 if it's just 1 or 0, basically. Eliminating the integral from the random equation make it computationally trivial, but it's a poor approximation. For example, the shadow created by V equal to 0 is perfectly black. It is common to attempt to minimize bias of direct illumination only approach by adding an estimation of the missing indirect illumination. So this ambient term, the ambient term may be a constant or a function of the normal. Function of the normal. Have any of you seen that? Like an ambient term that is not a constant?
This is new to me, but I guess you could.
Yeah.
I guess I'm picturing the diffuse term and the raster Phong stuff, but that's they're talking about ambient terms, so that's kind of not really.
Yeah, I've only ever seen just purely adding it.
To account for directional variant in direct illumination. Yeah, that sounds like was exploring in the early days with like OpenGL fixed function pipeline, this kind of stuff. But why we never heard of it? The ambient term is obviously another approximation. It cannot capture the richness of the full incident light field. In pseudocode, the direct and plus emitted plus ambient approximation just like this shader will win probably. LE is emitted readings, and we just have a for loop, and if this light is visible, we add its contribution. So it is still different from shader one because we somehow know how to calculate shadows. I guess this is a difference of this approach compared to pure rasterization.
Well,
Makes sense.
the basic, right? I mean, I think it's still just, is the light, are you pointing away from the light or towards the light, right? That's probably the only shadows that you're getting here.
They might be doing like occlusion as well, though, right?
You could, but then that's like a ray class, right? Basically.
Yeah. I think they are doing direct illumination, but at the point they cast a shadow ray. So there's a difference.
Whose Discord notification noise do I hear?
Yeah, it's probably mine.
Yeah.
I was like, wait, who's bothering me? Nobody. Oh.
Okay, that's
Some
what
ways
it is.
Come on. All right.
yeah. And some ambient approximation we just add to it. Note that in this code, finite scattering density will be 0 for scattering that would pass through the surface. It's a finite. Yeah, so there is no need to clamp the dot product of the outgoing vector and normal to 0. This allows our code to generalize later to include transmission and subsurface scattering.
I don't think I've ever heard of summand describing the inside of a sun.
I've heard
Never
add
heard of summand.
Yeah. I guess it's just like operand, right? But of a sum.
Yeah, there's a couple of words that are like that. There's also add end. That's yeah, not very commonly used terms.
Describe an everyday scene in which there is no direct illumination, yet objects is clearly have shading. That's just everything. Let's say if sunlight is only light, everything under the shadow is still clearly visible.
I guess would an overcast day count as well?
Yeah.
Because there's no direct path to the sun. But
Well, and there's probably very few direct paths from the sun that, it has to go through the atmosphere and
oh, right, true.
turn blue or whatever color, right? So,
Well,
yeah, if we count atmosphere scattering, there are no direct light to the sun. Definitely not.
I guess there's still one direct, the one.
there's a
at
few
least.
rays that get through,
Yeah.
There's a few that actually go all the way through the earth, probably too.
Oh, right.
A very low probability, but
Yeah, right.
so
Use your nose.
I think if you had a nuclear bomb, you can see it go off even if you're behind a lead plate or something, right? So,
Oh boy.
Yeah, I've heard that. Yeah.
with the atmospheric scattering, it's less turn blue and more everything but the blue gets bounced away kind of thing, or maybe the inverse of that. So it's more of you're seeing what light made it to you, where actually I think it's blue light gets diffused away or gets reflected away first in the atmosphere, which is why clear, you look up and it's blue, but during the sunset and sunrise, it's much more yellow and orangey because the sun has much further to go to get to you. And so the blue wavelengths of light bounce away.
Yeah,
it's
it's
kind
the
of
whole,
probably
whole-
like a prism, right? Like the rainbow.
Yeah.
it's the whole Raleigh and me scattering thing.
Yeah. Those are hella complicated.
Yeah.
Weighted retracing. So weighted retracing, aka backward retracing, or just retracing sample passes of the form LD question mark S star E. So it's just basically samples specular and has an optional diffuse in the past.
I guess it
Which is
doesn't have to be
direct-
specular either, though, right? The specular is optional, isn't it? So there's
Zero.
Yeah, specular is 0 or more.
so at most one diffuse, and then maybe specular. Okay, that's cool.
It's at most.
So you're actually
Yeah,
going
it's-
backwards, right? So it's the eye is on the right. So it's like a bunch of
Yeah.
specular bounces, and then eventually it hits some diffuse and stops, or it hits a light source.
And
Isn't
you're,
it-
and
isn't
you're
it
going
the
from
light?
diffuse to light.
I mean, because
directly.
you always do ray tracing from the eye to the light, right?
Well,
Most
Well,
times.
I mean, that's the weighted ray tracing. That's how it
Yes.
was done. Yeah.
yeah, and the diffuse question mark L, you do a lot of specular bounces, but once you hit a diffuse, that's when you go and sample your light rays to see if the light is visible.
That makes
Yeah.
sense.
Just diffuse surface.
This is when we just do the kind of direct illumination here.
Yeah.
But then I guess in the off chance that the specular perfectly points at a light, then you don't need the diffuse.
I mean, yes.
I guess
That's
what
actually the common case for those mirror ball images.
Oh, right, because like everything's specular, right?
You'd never hit a surface, so you're going straight up like that. Okay.
And
Yeah,
Yeah.
makes sense.
the classic Witten ray tracing image has a glass sphere in it, and
That's-
so it will diverge, have a translucent and a reflected ray coming out of the sphere.
That's the one that's always like a red and yellow grid,
Yeah.
right?
Yeah, with a red and yellow checkerboard in a glass sphere.
Visually, it produces reflection and refraction phenomena in addition to direct illumination. These are perceptually important and clearly identifiable phenomena of the image. At each point to be shaded, the weighted ray tracing algorithm computes direct illumination and then recursively evaluates instant light from at most two directions. These are the perfect reflection and refraction directions. To provide a base case for termination, the algorithm is typically limited to either a maximum number of scattering events or some minimum total transport along the light path, or both. Mirror and refracted light scatter at impulse in the BSDF, where f goes to infinity. Yeah, so perfect mirror doesn't exist because f cannot go to infinity. They also correspond to solid angle of 0 steradians. So instead of integrating the probability density of the scattering function, the equation for weighted ray tracing's approximation must be expressed in terms of probability mass. What is this symbol?
A rho?
Rho, yeah.
Rho, yeah. I feel like I need to know that, but I
Greek
haven't been
fancy
in school
tea.
for a while. So after a while, I just don't know how to pronounce it anymore.
So I don't understand why it's called probability mass.
Oh, you mean this?
Yeah.
Is
I
it
should
because
look
it's
that up.
not a distribution and it's just it's either true or false? So you have a probability of only two different options?
Yeah, so probability mass is for discrete probability.
Right, okay. Yeah, so
Yeah.
you're choosing either specular or
okay.
diffuse.
Yeah, so unlike BSDF, it's a distribution, right? So BSDF is a distribution function. It's not an actual probability. Its integral is a probability. And probability mass is, this row is actually just a probability.
Yeah, like for Witten style, like we look further down at the row mirror and the row transmit, it's literally going like, okay, a certain percentage of this is going to go reflect off the mirror and a certain percentage of it's going to transmit through the mirror, well, mirror-like surface. And then you just multiply that by the light contribution along those directions, and then you add them together, and so you know all the rows would add together to one, I think, in this case.
Yeah, it's those three terms contribution should add to one.
Yeah. Discrete versus continuous. In this case, it's discrete. Shh. I mean, sorry, bad joke.
Flow code implementation is clear and makes recursive limit explicit. So weighted approximation is the three terms. Direct, ambient, And the specular term is this is the use is like countdown.
It's interesting that the ambient doesn't need a bounces left -1 term because there's only up to one ambient.
Yeah.
Yeah. And go to here. There is another recast. That makes sense. Note that I is exactly the function that render evaluate at the center of each pixel. I've just added the bounce left argument to ensure the finite recursive depth. Yeah. Also note that if every surface in the scene is both reflective and transmissive, then the runtime for a single pixel is O2 of bounce is left. Yeah, so this is the problem of weighted ray tracing is that it is simple until you have a lot of this kind of material, then it's just explode.
Well, it seems like any algorithm would explode in that case. The vase full of marbles.
Well, if you wanted to
brute force
convert
path
it, might take
tracing,
a lot of time.
it will not explode because it will only sample one path.
Right, but you get noise.
Yeah, they get noise instead. Weighted ray tracing extends direct illumination and is built on recursive recasts. Path tracing, bidirectional path tracing, and photon mapping all continue to extend this approach, which is currently dominant in realistic rendering. Radiosity and the metropolitan class transport algorithm follow are very different approaches. Path tracing, I guess those tools are the algorithms he talked about before. Unfortunately, I only heard about them, the names, and never understand them.
Yeah, I think radiosity was like you kind of like from every surface you figure out like how much of all the other surfaces you can see, and you make this giant equation of like you know, how much each surface can see each other surface, and then you try to solve that equation to figure out the global illumination. That was the original idea.
Yeah, I think you like divide the surfaces into patches and then like transfer energy between patches.
Yeah.
You can view the patches in Source Engine because they use radiosity for global illumination, and you can like change the resolution of it in the editor. It's kind of interesting. Yeah, it takes forever to compile maps.
Yeah.
Suggest path tracing algorithm extend weighted recursive ray tracing to sample indirect paths that are not necessarily specular. Yeah. For like have multiple diffuse bounce weighted just failed. it treated a set of transport passes through the scene that all share a common backbone, but at each node fork one ray twitch light source for direct illumination. Forking only a single terminal ray at each node holds a branch factor of 1, yet is theoretically able to sample any light path. Instead of choosing the recursive path to be the specular impulse, the path tracer randomly selects the direction at each surface hit. Ideally, one would choose the direction proportional to the amount of light scattered so that computational work is performed in direct proportion to the energy contribution to the image. Since the amount of scattered light is unknown while the path is being traced, in practice, one
yeah, it's supposed to be one.
I think it's
yeah.
1. In practice, one usually samples the direction to trace light backward along its path based on the BSDF's probability density.
That's the important sampling, right?
Yeah.
I think that's what the Metropolis algorithm is about, is doing importance sampling.
Yeah.
I've never read that paper though, so I don't know.
We should read that someday. If it's a paper, we can just take a week to read that. Because path tracing begins at the camera and work backward, it is inefficient for discovering caustic paths. Those paths depend on the position of light. So an algorithm that searches backward from the camera is unlikely to discover a specular reflection into the light. What's a caustic path again?
It's like a projection through a surface or off of a surface onto another surface.
Right. So you have to do a specular directly into the light.
Yeah. So like this.
Yeah. This probably is much easier to find diffuse rather than specular passes. To caustic will look too dark without a lot of samples.
So you could have like a really complicated light source, right? Like if you have a like a pinhole camera and you're trying to, like for like when you have an eclipse of the sun, right? You don't want to look at the sun, and you can poke a point into the paper and then you can project it onto the ground or the wall or whatever. But that's a very complicated caustic, right? Because it's actually like an image that you're projecting instead of just a point source. So I mean, I think that just the level of complexity that you can have, it can go very high.
And bidirectional path tracing. Bidirectional path tracing addresses the limitation of path tracing by tracing two trees and then connects their leaves. One tree is from the source and one is from the camera. The tree from the source is able to capture the caustic passes that are undersampled by path tracing. The path from the camera is able to capture the specular reflection and refraction seen in ray tracing. Collectively, they cover all passes, including specular nodes with high probability, as well as passes with diffuse nodes. Any two random subpaths are unlikely to ever meet exactly at the same terminal node. So the two trees are not connected and no complete source to camera paths are formed during the tree search. The most straightforward way to connect the passes is to take n terminal node and cast ON square explicit shadow rays between them. Since n nodes that leaves full tree of depths k and m initial paths from each of the light and camera, there are all n times k square total ray trays to connect the passes. OM square if only terminal nodes are connected. And to read this again. N terminal node. N square. Yeah. Tree of depth, K and M initial pass. That's what?
It's a very complex thing. I'm looking at like how do you implement this? And the answer is with difficulty.
And bidirectional is complicated, yeah.
It's like you're computing where the light goes, and then you're computing where the camera is looking, and then you're just kind of like connecting the dots, but there's going to be many dots.
So we kind of
Yeah.
actually do this when we're doing shadow maps, right?
Ooh.
You're
Ooh.
doing the forward light to make the shadow map, and then looking at it from the other way.
That is a good analogy.
Yeah. Yeah, it is unfortunately somewhat challenging to implement because of the connecting passes in the center. Also, the way that light is being sampled compared to a trivial random direction sampling. Yeah, and how to sample those? Compensating for that to avoid biasing the solution require very complex term in the math and program. Retracing with photon mapping provides some of the theoretical advantage of bidirectional path tracing, yet produce lower variance and is much simpler to implement. Photon mapping is a consistent estimator of the illumination because as the number of photons approach infinity, the estimate converts to the correct illumination. Yeah. However, unlike bidirectional path tracing, photon mapping is biased because for any finite number of samples, it may approach to a limiting value from a strictly positive or negative side, depending on the scene. So, how is bidirectional not biased? An unbiased estimator has a correctly expected value. I see. Independent of the scene of any number of samples. In fact, more important for entertaining applications, the results are often more aesthetically pleasing than those of path tracing for any given number of samples because bias is often less noticeable than noise. Yeah, who care about bias? Do we need to explain the bias and
I would love
correctly
a
expected?
more detail on biasing.
Yeah, I'd like to get a firmware handle on what exactly we're talking about when we say bias. Yeah.
Yeah, I think it's just this sentence. An unbiased estimator has a correct expected value independent of the scene for any number of samples.
So it
So,
works nice.
so even if for path tracing, even if we only just have one sample per pixel, on average it is correct because its expected value is the correct converted value. That's why we say it's unbiased. But he's saying with photon mapping, that is not the case. It eventually will be correct. That's why he says it's consistent. But if we have one sample, it can be biased toward a certain direction.
Oh. Hmm.
The key idea of photon mapping is to avoid the O(n)² connecting cost from bidirectional path tracing. The algorithm proceeds in two steps. The first step traces photon passes from the source in a style similar to path tracing. From the source, you mean light source. So from here, each photon is stored at every surface that it strikes along a path and is either absorbed or scattered. The result is a set of nodes along the path of many photons. The second step, path trace from the camera. At each point, it computes direct illumination and then estimate indirect illumination from all nearby photons. The nearby photons are identified using a spatial data structure such as KD tree or hash grid. Can we use BVH? I don't know, but yeah, but BVH is not spatially partitioned.
I think for collisions, you can use the PVH, probably.
I think
But,
BVH is more broad, right? Like a KD tree or a hash grid are both BVHs. Because it's just
no, it's
bounding
different.
volume, right?
So some acceleration data structures are partitioned by objects. So BVH partitioned by objects, and some partitioned by space.
Can you consider like a octree? Like, couldn't that be a BVH? Because it's, the volume that everything inside is bounded by. I thought BVH is more of a general term, just describing all of these different.
I think you're right.
I think maybe, but I think usually when we talk about BVH, we're talking about balanced BVH. Right?
Well, I guess the important part of the BVH is it's bounding, right? So if like it's like an octree, maybe a thing could be on both sides. If it's if it's a true like binary
Oh yeah, that's true.
subdivision.
Yeah, so for BVH, we usually partition in a balanced fashion to make the left and right roughly equal. That's why we say it's partitioned by objects.
Yeah, like a voxel or a octree, it's more optimized by traveling through it, right? Like if you had a ray traveling through it or something. What's that? I don't remember the name of the algorithm for traversing an or a voxel.
Oh, DDA.
That's one of them. Yeah.
So it looks like maybe octrees would fall under a space subdivision algorithm rather than.
Oak tree is similar to those two, not like BVH. The key step is the radiance estimation from photons. At a point x and outgoing directional omega 0, the scattered indirect light is estimated from nearby photons by something. What is this?
Phi.
This,
Phi.
yeah, phi.
Phi photon.
Where phi j is the power of the j's nearby photon. Power of j's nearby photon. And this is sum of all the photons, all the nearby photons. And omega j is direction from which it came. R is the radius of the sphere that defines the boundary of the nearby region of the space. And this F is just a BRDF. That makes sense. To smooth out the result, one typically fade the contribution of the photon out. Fade the contribution of the photon out. That's why R is a constant. Has a distance from x to the location that the photon heat increases.
Is that kind of giving an idea of like the inverse square law kind of thing?
Yeah, but where in this equation is that? Because I don't say that.
Is it the r squared in the denominator there, or?
Yeah, but R is a constant, right? R is the radius of the sphere that defines the boundary of the nearby region. So I don't know.
Seems like a bug in the text there, or in the equation.
Yeah. So this is another paper that we can read.
Certainly
I feel like for those kind of things, it's like graphics codex is really brief, and we really need to delve into it to understand. Not like just read those 2 or 3 paragraphs and suddenly we just understand how the whole algorithm works. But it's a good survey. The radiosity algorithm uses a different approach than ray-based method. It's assumed the scene contains only Lambertian materials. Yeah, that's what I heard. In such a scene, the only passes to consider are the form of LD star E. Just everything is diffuse. Then the scattering function are defined by a single reflectance constant. The algorithm is applied to large patches, e.g. triangles instead of points, and consider the power transferred between them. And calculate a closed form solution. By the way, it's an hour and 20 minutes. Do we want to stop here?
No, we're
It's
almost
not too
done.
much. Yeah.
Just hit a
One
nice stopping point.
paragraph.
Yeah, you just finish it up.
The algorithm is applied to large part. Yeah. Under this framework, the radiosity Bx leaving patch X is the sum of the radiant emitting Ex at the patch and the radiosity By due to every other patch Y that is scattered toward X, modulated by the reflectivity rho X at X and the form factor between Y and X. What is the form factor? The parallel to random equation. The form factor takes into account of projection of the patches out to each other. Okay, so this is kind of like the similar to the cosine term in the random equation. It decreases with distance and angle between them.
Seems like you'd have to take into account visibility too.
Yeah. In linear algebra notation, we can express a relationship between all B values by creating a long vector of the radiosity leaving each patch and the matrix of the form factor. Yeah.
Could you do the visibility in that form factor?
Yeah, probably.
I don't.
I mean, you could say that it's part of that value. Yeah. What's F?
I think that's the form factor, right?
Oh, right.
Okay. Yeah.
Yeah.
As in random equation for L, this equation created a recursive relationship in which the net radiosity vector B is defined in terms of itself. Yeah. We are solving this equation basically. If they evaluate it, if we're computing the sum of the direct elimination, single scattering interaction, double scattered interaction, etc., etc. Each term in that sum has a reflectance and form factor applied multiple times, and thus give an infinite sequence of increasing matrix powers. Instead, there's a closed form solution for expression of this form in linear algebra. B is equal to E plus. Yeah. But yeah, inverting a matrix is costly. We don't need to invert the matrix though. We can just solve it directly with Gaussian method or something, which is a little bit less than a third. However, this computation is amenable to a number of methods for approximation solution to a linear system that will need significantly less time. It is of historical interest of Goro's paper was to first to feature the empty Cornell box and compare the render result to an actual photograph. Makes sense. Radiosity tend to work well for architectural scenes and area emitters. Yeah, because it works with patches. Because architectural scenes are often designed with primarily matte surfaces and slowly varying illumination in order to help occupants navigate the space safely. Consider the alternative design, a set of hallways with pin light sources and a lot of reflections that is confusing in the manner of amusement park house of mirrors. Yeah, that would be bad. Why put a single table in the end? Yeah, anyway, we're done. And a lot of people to read. I don't know if we are going to read this one, at least not now. I think this one, we read this one. Yeah, this one and this one. What is this one for? Let's stop recording first.